Hello everyone. I would like to talk with you about the review and how to study for our final exam. So I gave you a review sheet that just has a list of topics. And the reason it has only a list of topics is you can find similar questions for each of these topics on previous tests. So that's what you should look over is previous multiple choice questions. At the same time, you can make a sheet of notes front and back, and you can write whatever you want on that piece of notes to help you. So what I'd like to do in this video is I want to run through this review sheet, and I don't know if this will turn out to be one video or more than one, but I'd like to give you some tips and tricks on reviewing each of the topics and what you might choose to put on your review sheet for the exam. So without further ado, here we go. So there's a couple of key things you need to know about circular motion. The first thing is you should know the direction of the force, velocity, and acceleration vectors. So if something is going in circular motion, so let's say that we had a record player turntable and we sat something right there, and it was going around and around, then the velocity vector always acts tangent, and the force vector and the acceleration vector always act towards the center of the circle. Let's change the position now. Let's pretend we have a car traveling down the road and the car goes through this big dip. And so that big dip is part of a circle. And so if the car was at the bottom of the dip, its velocity would be tangent to the circle, and its force and acceleration vectors would both be pointing upward. So depending on where the object is, they could be pointing in different directions. So be able to do that. The second thing is that we need to know what provides the centripetal force. So here's some quick examples. So if we had a record turntable and we sat something on the record turntable like a penny, like what would hold it into place? Like what is holding that penny in its spot? And the centripetal force would be friction. What if we had somebody riding the rotor? And so here is their body and they're like stuck to the wall. There's got to be a force going towards the center of the circle. And what would that force be? It's the normal force that holds that person into place. I'm trying to think of another one that we did. If we had a stopper, we were swinging the stopper around and around, and the stopper was right here, and we had it tied to a string, it would be tension in the string that was holding the stopper in place. So just some key things there, and you can go back through your notes and look through some of those also. But it's a little bit more complicated if something's going in a vertical circle. So let's do a vertical circle. Let's call this like a roller coaster, and something's coming down and going into this vertical loop. So if we had the roller coaster right here, like upside down in the vertical loop, we have FW pointing towards the center of the circle, and coaster pushes on track, track pushes back on coaster. We have FN also pointing to the center of the circle. And so when we use the centripetal force equation, mv squared over r, the centripetal force means like the net force that's going towards the center of the circle, and that would be Fn plus Fw equals mv squared over r. We don't have to solve that equation for anything right now. We just need to know how to write the mathematical relationship. Let's do another example. Instead of a car being at the bottom of a hill, let's make the car be at the top of the hill. All right, so if the car was going over a hill, that hill is again part of a circle. I still have FW going down, but car pushes on road and road pushes back up on car. I know the arrow pointing towards the center of the circle always has to be the biggest arrow. So when I do FC equals mv squared over r, the net centripetal force is going to end up being FW minus Fn equals mv squared over r. So those are two key examples that you might want to put on your notes to kind of help you remember. But the key thing is that you always replace the centripetal force with what's going towards the center, and it could be both things. And if it's only one thing, the longer arrow always has to be the one towards the center. All right, next, let's look at the topic of work, power, and energy. All right, so one of the things we need to be able to do is write an equation to calculate work. So work is always force times displacement. But the F has to be in the same direction as the displacement. So some things you might want to put on your notes. So let's say that we had a box and we were pushing the box with a force in this direction and the box was moving that way. Then we might say that the work is equal to like FA times D. If we had friction in the story, then it might be FA minus friction times D. But what if I was pulling the box at an upward angle like this, FA, and then the box was going this way? Well, then I need the force that's going in this direction, and that force would be Fx. So then the work would be Fx times D, and Fx would turn out to be Fa cosine theta times D. And if I had friction, then it would be Fx minus friction times D. And let's do one more. Let's say that I was lifting a box. Lifting. And so the work would end up being equal to the force in the direction of the lift, which would end up being the weight of the box, and that would turn out to be mg times the distance that I lifted. I think if you know those three, you'll be in good shape. All right, the next one, recognize units of work, energy, and power. So units of work could be, I'll say work, could be the joule. But work is also equal to F times D, which means I could write a joule as a Newton meter. That's also a unit of work. In terms of energy, we know that energy can be in joules, but we should also remember that special kinds of topics have its own unit of energy. So when we talked about electrical energy was in kilowatt hours for energy. For food, it was in calories. And for nuclear energy, it's in electron volts, which we can convert to mega electron volts. So those are all units of energy. And power is measured in watts. All right, calculate the power when lifting something. So if I wanted to calculate power, power is equal to work over time. And the work that I have done would be FD over time. And if I'm lifting something, that F is going to be mg times D over time. So if I plug in the mass times 9.8, the height that I lifted divided by time, that's going to give me the power. All right, the next topic says calculate total energy and determine the potential and kinetic energy for any spot on a roller coaster. So let's just make up a roller coaster here. We'll go like this, we'll go like this, and all right, so the motor does work to get the roller coaster to the top of the hill. Let's pretend the roller coaster does 600,000 joules of work. So that means that the ET of the coaster, the total energy, is going to be 600,000 at all times. So when the roller coaster is at the top of the first hill, which is this high, it is all potential energy. That means all of this work is potential. So I'll put down 600,000. 1, 2, 3. And I have no kinetic energy. That means the roller coaster is temporarily perched at the top of the hill. And now it goes over the top of the hill, and assuming it goes all the way down to almost skimming the ground, all of that potential then is going to turn into kinetic, because I won't have any potential, and now it's all going to be kinetic. So let's say that you knew the height of this hill. You now could calculate the potential energy at the top of this hill, and then you could subtract from the total energy, the 600,000, to find the kinetic energy. You would know what that value is, and then you could set that equal to 1/2 mv squared to calculate the velocity at the top of that second hill. So know a little bit something about roller coasters. All right, the last one is apply conservation of energy to a swinging pendulum and a firing rocket. So let's do a swinging pendulum first. So we'll tie something on the string, and we're going to make it swing back and forth like this. So it's going to go over here. So when I look at a swinging pendulum with conservation of energy, we can have an H equals 0. I'll call that here. And you can see that it goes up a certain height, H. So I'm just going to make up a number here. So let's pretend it goes up 0.4 meters. So over here we'll call this spot 1. So at spot 1, my object has potential energy, and then it's going to swing down, and all that potential down here is going to turn into kinetic. That's assuming I make my H equals 0 at the bottom there. And we find out that the mass of the object doesn't matter, but if I know the height, whoops, that G becomes a 9.8, and the height is 0.4, equals 1/2 v squared, you can now solve for v to find the velocity of the object down here at the bottom at spot 2. Similarly, you can also do the same for a rocket being fired upward. So let's pretend that this is my ground. I'll put this dot here that's going to stand for the rocket, and now I'm going to fire it upward, and it's going to go to the top. It's going to stop at the top because the velocity became 0. So at the very bottom, at spot 1, I'll call this potential plus kinetic at spot 1 equals the potential plus the kinetic at spot 2. By the way, I could have written this the same way up with the pendulum, but I think this might be easier to explain it this way. At spot 1, I don't have any potential, but I am firing it up with a pretty big velocity. So I would have to know what that velocity is. And then it's going to go up, and it's going to have potential energy, but it's not going to have any kinetic because the velocity is 0. So if you tell me the velocity, whoops, the mass doesn't matter. So if you tell me the velocity that I fire it, I can then solve for how high up it goes. And that's what I'd like you to be able to do. All right, the next topic is momentum. So we need to know the SI units of impulse and momentum. So impulse, the equation for impulse, or the variable of impulse is J. It's equal to Ft, and momentum is equal to mv. So the units are going to be newtons and seconds, and these units will be kilograms and meters per second. All right, state or recognize examples of impulse. So the classic examples of impulse are using time to decrease force. So if I can make something happen longer, I decrease the force. So for example, if I'm going to jump off the roof of a building, I could jump onto the concrete and then I would go splat. That would be a big force. But if I jumped into a trampoline, then the time that I would be landing would be longer and my force would be less. We talked about that was the purpose of the airbag. That's the purpose of why we cradle a balloon when we catch it. So those kinds of examples of impulse. All right, calculate impulse momentum and apply the impulse momentum theorem. So to calculate impulse, obviously I'll use that equation. To calculate momentum, I'll use that equation, but they're also equal to each other. So I can say that impulse equals momentum. So if I knew the force acting on something, I'll just make up the example, 10 newtons in an x for 20 seconds. Then it can act on the mass of an object. We'll say the object is 3, and then we'd be able to calculate its change in velocity. So a question similar to that. All right, apply conservation of momentum to determine the resulting velocity after a collision. All right, let's make one up. So let's pretend that we have a mass that's traveling this way. I'll just make up some numbers. So the mass is going to be 3 and the velocity is going to be 4, and it is going to have a head-on collision with an object of mass 2, and its velocity is 3. And then, because they're, I'll say, both sticky, they're going to end up sticking together. And then what is the final velocity if they stuck together? So I'm going to go mv plus mv equals mv. So this would be 3 times 4, but here's the catch. You need to remember that when something is going in the negative x direction, we have to make the velocity negative. This mass is the mass of the stuck together objects, so that's going to be 3 plus 2, that is going to be 5. And I'm actually solving for this velocity. So I have 12 minus 6 equals 5 times v, so it's going to be 6. So whatever 6 divided by 5 is would be the final velocity of that. So the key thing there is to remember that velocities can be negative. All right, state facts related to elastic, inelastic, and perfectly or totally inelastic collisions. All right, so we have elastic collisions. We have inelastic collisions. And then we have perfectly or totally inelastic collisions. All right, in all cases, momentum is conserved. Momentum is conserved. Momentum is conserved. But if it's an elastic collision, kinetic energy is conserved. Kinetic energy is not conserved in these inelastic collisions. And if something is perfectly or totally inelastic, that is the only time the objects stick together. That's the defining characteristic of perfectly or totally inelastic collisions. All right, the last thing, determine impulse or momentum from a graph. All right, so from a graph. So if I have a graph of force versus time, let's just make up some example here. We'll go like this and we'll go like this. So let's call this a force of 10 newtons, and we apply a force of 10 newtons for, let's say, 8 seconds. and then the force starts to decrease. All right, so if someone asks you what the impulse is equal to the area under the curve. So we can figure that out very quickly. So 8 or 10 times 8, so this part here is 80. And this part is 1/2 the base, which is 4, times the height, which is 10. So that is going to be 40 over 2 is 20. So the impulse would be 100 Newton seconds. But because of the impulse momentum theorem, impulse is equal to momentum. So that also tells me that the momentum is 100. And if I knew the mass of the object, then I could calculate the change in velocity of the object. So just be able to get impulse or momentum value from the graph. Okay, the next topic is oscillations. And we're supposed to know why there's a negative sign in Hooke's law. We're supposed to know our spring facts and energy relationships and something about a pendulum. All right, let's start with the spring. So let's pretend that we had a table, and we'll have a wall here, and we are going to tie a spring on it, and we're going to put a mass on the spring. All right, so this is just at rest right now. If this is at rest, this would be the equilibrium position. But now I'm going to take this mass and I'm going to pull it, meaning I'm going to stretch the spring even more. So over here, we're going to call this an end point. So let's work with the end point first. So first of all, I pulled this a positive x value. So I'm going to write down plus x. And now that spring has a force in it. And the force in a spring is called the restoring force. And it wants to go backwards. It wants to go back. So there's a negative sign there. So in Hooke's law, we have F equals negative kx. And this negative sign means that whatever way you pull it, in the x direction, the force wants to go back where it was or in the opposite direction. So if the restoring force is at a maximum, which it is over here at the end point, it means that the acceleration also wants to go back, and the acceleration is also at a maximum. And if I have it over here and I'm holding it, it also has maximum potential energy. Maximum potential energy. And because I'm holding it, I'm going to put a line here. Because I'm holding it, the velocity is 0, which also then would mean that the kinetic energy is 0. All right, now I'm going to let go. And when I let go, it's going to boing back. It's going to pass equilibrium, but it's going to actually keep on going. And when it keeps on going, it's going to scrunch the spring up over here when it's here. And then it's going to keep on going back and forth, back and forth, back and forth. So everything that is true about this endpoint would be true about this endpoint. But what about when it's passing equilibrium? So when I let go and it passes by equilibrium, it's going to be going the fastest when it passes this equilibrium. So I'm going to write down Vmax. So that's the maximum velocity. And if its maximum velocity is happening here, that would also mean that it has its maximum kinetic energy at this spot. I'm going to put a line here. So x equals 0 when it's at equilibrium. And that means the restoring force is temporarily 0. So that means the potential energy is 0. And so these things always kind of like work together in groups. So the V and the kinetic energy are the same. And you can see they flip-flopped positions here. In this group, whoops, I forgot the A here. If the force is 0, the acceleration is 0. And then this group will end up flip-flopping over here. And so that's one way to learn and to memorize your spring facts. All right, so if I had to graph that out, so let's do a quick graph here. So what if I wanted to graph? Here's equilibrium, and here's an end point, end point, end point. What if I wanted to graph the potential energy over time? So let's put potential energy right here. Potential energy. So at equilibrium, the potential energy is 0. And at the endpoints, it's at a max. So let's put a dot up here at the max and a dot here at the max. I just want to remind you that the equation for potential energy is 1/2 kx squared, where k is the spring constant. And I have this x squared. So that means that I don't just connect this, but it's a parabola, x squared. So it ends up looking curved like that. And if I did the same sort of graph for kinetic energy, so we'll put kinetic energy here in the middle. Kinetic energy is at a max at equilibrium, but kinetic energy is 0 at the endpoints. But that equation is 1/2 mv squared, so still got the squared going on. So it ends up curving down like that. So it would also be helpful to have those graphs on your notes or to be able to reason those out. All right, next we're talking about fluids. What do you need to know about fluids? So the first thing is that pressure equals force over area. So you should be able to calculate the pressure acting on something. So the pressure acting on something is going to be like the weight of the person. So mg, the weight of the person, divided by the area that they're standing on. And they're going to be standing on something that has length times width. Length times width. So you can calculate the pressure that acts on something. That's the second dot or box on your review sheet. All right, the next thing is to be able to differentiate between absolute and gauge pressure. So how do you calculate the gauge or the absolute pressure acting on something? So the absolute pressure is equal to the atmospheric pressure plus the gauge pressure. So if someone tells you that they puffed into a balloon with 100,000 pascals, and then we want to know what the absolute pressure in the balloon is, it's not just what we puffed into it. We would also have to add on the 101,325 so that we know the absolute pressure. You can also do this in pounds per square inch or PSI instead of pascals. So what if I puffed into a basketball 10 PSI, pounds per square inch? We would then have to add on what is the atmospheric pressure in pounds per square inch. And that number is 14.7 pounds per square inch. And that would give us the absolute pressure. So know how to do it in pascals and pounds per square inch. All right, the next thing, determine the absolute pressure underwater or when the wind is blowing. So let's call this the top of the water. All right, so we are going underwater. So we're going down this deep, we'll call that H, that's how deep we're going. So the pressure that acts on somebody underwater is going to be equal to 101,325. But when you go underwater, the pressure on you increases. It increases. You have to know that's a plus. And it increases by this amount, PGH, where this is the density of the fluid. That would be 1,000 G would be 9.8. And then H would be how deep you're going under the water. What about when the wind is blowing? So we did a picture of a house. I'm just going to draw a little flat house. And we had the wind blowing across the house. And so to find the pressure above the house, it's 101,325. But it's minus the pressure. When the wind whips, the pressure dips. So I have to know this is a minus. And how much is the pressure going to dip by? This is Bernoulli's equation. It's 1/2 PV squared. So it's going to dip by 1/2. And this is the density of the fluid. This time it's air, so it's going to be 1.29. And then V squared would be the velocity of whatever the wind is. All right, determine the effects of the buoyant force. So we don't need to go real deep into this, but let's say I had an object. I'm just going to put 2 kilograms. And so it's FW. FW would be mg. So that's going to be 2 times 9.8. That'd be 19.6 newtons. So if I have this object in air, it weighs 19.6 newtons. But now if I dip it underwater, the buoyant force appears. And the buoyant force is equal to PVG, the density of the fluid, 1,000, times the volume of the object, times 9.8. And all I need to know is that the buoyant force is going to make it weigh less. And I'm just going to make up a number. So if the buoyant force happens to be 3 newtons, now the object is going to have a new weight. We'll call it the apparent weight. And that'd be 19.6 minus 3. That'd be 16.6. When I dip something, it's going to weigh less. That's all you need to know. All right, explain how speed varies when the path narrows or widens. So let's use a river as an example. So we're going to have a really fat river here, and then the river is going to narrow. Fat river, the river narrows. Or you can call that a pipe. Fat pipe, skinny pipe. But we have water flowing through this. So all you need to know or memorize is that the water velocity here, I'm just going to make up a number, could be 2. But when something narrows, the same amount of water has to pass through the narrow spot that passed through the fat spot. So the velocity has to increase. So maybe the velocity now is 10. I'm just making up numbers, but the velocity here is always faster in the narrow section. All right, next is electrostatics in circuits. Know the difference between the electric force, this is an F, let's scribble it out. So the electric force is going to be K, QQ, over D squared. So the electric force is the force of attraction or repulsion between 2 charges, times K. K is 9 times 10 to the 9, divided by their distance squared. And we can compare that to the gravitational force between 2 masses, where we have a constant of 6.67 times 10 to the minus 11. And it's just looking at the symmetry of those equations, knowing what the variables stand for, and also knowing that Fe, the electric force, is always way greater than the gravitational force. All right, as we talk through circuits, we're just going to be a little bit generic here. This topic is relatively recent, so I think we'll do okay. Choose a wire with the greatest or least resistance. So let's say great and least. So great resistance, least resistance. All right, a wire that has a lot of resistance, like a bad wire. Electrons don't like it. They don't like skinny wires, and they don't like long wires. That has a lot of resistance. And we can kind of reason that out from this equation. This is the resistivity, means what the wire is made out of, and the length of the wire, and then this is the cross-sectional area of the wire. The least resistance, like what do electrons like? They like fat wires that are short. And that same equation applies to that. All right, explain how current varies in a circuit. So let's just kind of make up a circuit. Make up a circuit. All right, so again, we're just going to make this up. So let's go like this. Let's go like this. All right, let's put our battery here. Let's put a resistor here, and then let's put a resistor here. And I'm just going to make up numbers. Let's go 8. Let's go 12. And let's go 6. Okay, so explain how current varies in a circuit. So current is going to come out of this battery, and it's going to come around. Let's put a resistor here. All right, so all of the current goes through the 2, and then it comes over here. And now some of the current's going to go the 8-way, and some of it's going to go the 12-way. So what I want you to be able to reason out is which way is most of the current going to go. The current always wants to take the path of least resistance. So there's going to be more current that goes the 8-way and less that goes the 12-way. But it's not all going to get to go the 8-way. And then, so some goes the 8-way, most of it goes the 8-way, some goes the 12-way, and then it comes back together here, and then all of the current passes through the 6. So there's a multiple choice question, kind of like reasoning out where more of the current is going to be. All right, so how could you determine which light bulb would be the brightest? The brightest light bulb, I'm going to write down brightness, equals current. So whatever resistors, assuming these resistors are all light bulbs, whatever ones have the most current going through them are going to be the brightest light bulbs. So all the current goes through the 2, here it splits, and then all the current goes through the 6. So the 2 and the 6 are going to be the brightest bulbs, and they're going to be equally bright. And then, if I had to compare these two, there's going to be more current going through the 8. So he's going to end up being brighter than the 12. And I would write it that way. All right, last thing, calculate the equivalent resistance, current flowing from the battery, and maximum power. So if I told you that the voltage was 20 volts, I would just want you to be able to find the REQ of this circuit. You can draw the pictures or not draw the pictures, that's up to you. And then you can apply VIR to find the current coming out of the battery, and you can apply PIV to find the power delivered to the external circuit. All right, and next let's talk about some things about waves that you should know. You might want to go back and review the Schoology quiz on waves. So given a wave, determine the wavelength, amplitude, frequency, and velocity. All right, so I need to draw a little neater. All right, we'll try this. All right, so we're going to call this 10. I'm going to call this 20. And we're going to call this 5 and this 5. All right, so we'll pretend everything's in centimeters. All right, determine the wavelength. The wavelength is the length of a complete wave. So wavelength equals 10 centimeters. I might want to write that in meters. So 0.1 meters. All right, what is the amplitude? The amplitude is how high is the wave. That would be 5 centimeters or 0.05 meters. Determine the frequency of the wave. I should have added period to that list. So let's find the period. The period is all right, next let's look at frequency. In order to get frequency, I need to know how long it took for this wave to pass. So let's say this happened in 2 seconds. So frequency is going to be how many waves passed per second. So I'm going to count them. This is 1 wave, 2 waves, and this is a quarter wave. So 2.25 waves passed me in a time of 2 seconds. So 2.25 divided by 2 is 1.125 hertz. If you care about period, period happens to be 1 over f. So 1 divided by that number would be the period. That turns out to be about 0.89. All right, but the last one was velocity. So velocity, I mainly wanted you to remember this equation. This is the main equation for waves. It's frequency times wavelength, but you have to remember that everything has to be in meters and seconds. So frequency is 1.125 hertz, and a hertz is a 1 over second, so we're good there. And the wavelength has to be in meters, so 0.1. And so we can then multiply that, and the answer would be 0.1125 meters per second. Probably not realistic, but that's the wave, I guess, that I drew. Okay, next, state some properties of waves. So I just want you to recognize the words and know what they mean. So the first word is rectilinear propagation. And I can't talk and write at the same time. Rectilinear propagation. And that just means that waves travel in a straight line, and we can draw them as arrows. Reflection. Waves reflect from a boundary, just like when you play pool and the ball bounces off the pool table. Refraction. Refraction is when a wave appears to bend when it enters a new medium, like going from air into water. Diffraction is when water or when something bends around a barrier. So when water goes through a hole and then it kind of curves past the hole, or when you can hear a sound wave around the corner of a room. And then we talked about interference. Interference is what happens what happens when a wave overlaps, and we specifically looked at 2 stereo speakers sending out sound waves, how they overlap. We have areas of double loud sound, regular loud sound, and there could be areas, or there would be areas of no sound if we could block out the reflections from the room. All right, so look over those pictures and look over that section in your notes. All right, next one, state some key facts about sound. So we should know that the velocity of sound can be calculated by 331 meters per second plus 0.6 times the temperature, assuming that temperature is in Celsius. So that's how the speed of sound varies with temperature. If we're talking about room temperature, the speed of sound is 343 meters per second. Sound also travels fastest in solids than in liquids, and liquids are faster than gases, and that's because of the spacing of the particles. Some other key facts about sound. Humans can hear sounds from about 20,000 or 20 hertz up to 20,000 hertz. But there's some sounds that we can't hear. Those are infrasonic sounds. But some animals can hear them. And there's other sounds up high that we can't hear, high-pitched sounds, and those are ultrasonic sounds, but some animals can hear them. All right, we should know a couple of key vocab words that when we talk about loudness, we might disagree whether something is loud or not. But in physics, we can calculate the loudness, and it's called intensity. And so we can kind of like mathematically quantify the loudness. And intensity is measured in decibels. That's the unit. We can also talk about if a sound is high-pitched or low-pitched. And we might disagree whether it's high-pitched or low-pitched, but we can turn it into a number by talking about its frequency, like we did up here. And so frequency is measured in hertz. And frequencies also correspond to musical notes. All right, the last thing I think we should review about sound is the Doppler effect. So the Doppler effect is that you hear a change in frequency due to the motion of the observer, who is the listener, and or the source. So for example, this would be the velocity of sound, this would be the velocity of sound, those would both be 343. This is the velocity of the observer, who is the listener. This is the velocity of the source. And then the signs are plus, minus, minus, plus. If the listener and the source are getting closer together, you use the top. So I'll write down top equals closer. And if the source or the listener and the source are getting farther apart, we use the bottom signs. But more importantly, we're probably not going to have to number crunch on the exam. You just need to know that the frequency that somebody hears could be higher or lower depending on where they are. All right, the next one is list the waves of the EM spectrum in order of increasing energy. So I'm not going to write them out, but I'll abbreviate them. So at the very bottom, the lowest energy is power, then radio, then we would have microwaves, then infrared. Infra means before. Now we have visible light, which is the Roy G. Biv. That tells me that violet light has more energy than red light. And then violet, then we have ultraviolet, ultra meaning after violet. And then we have X-rays, and then we have gamma rays. So we should know that this means that the energy is increasing as you go across that chart. key scientists associated with what is light. So I'll talk through them briefly. So we started the what is light with Newton. And Newton believed that light was a series of particles. And he wrote about this in his book called Optics that he published after he published Principia. So light was a series of particles. And then we had another scientist who was not as well known, and his name is Mr. Huygens. And Mr. Huygens proposed that light was a wave. But people were hesitant to disagree with Newton. And so things kind of went on, and we collected examples of light being a particle. We've collected some examples of light being a wave. And then we had a key experiment by Mr. Thomas Young that showed that light would create light in dark bands, and that had to be an example of diffraction and interference, which were known wave properties. So there was a switch that, people kind of went to the wave side. And then we have Mr. Planck. So Mr. Planck came on board. I hope I'm not missing anybody in the story. But Mr. Planck, he was the one who came up with the equation E equals hf, h being Planck's constant. He said that every frequency is associated with a certain amount of energy, and that light was quantized. So without explaining that in further, it was another example that light had to be a particle. And then we have Einstein come on board, who agreed with Planck. And he even said that these particles that we're talking about, he gave them a name. He called them photons. So if you have a light particle, he called that a photon. Then we have Mr. Millikan. And Mr. Millikan did not like Einstein. And so he tried to prove that light was a wave. He tried to disprove Einstein. And he tried for 10 years, and he kept failing. So all he did is further provide proof that light was a particle. And so we just have this, fight that goes on for, I want to say, 40 years. And then it kind of came to a head when Mr. Niels Bohr said, we obviously have evidence of light being a particle. We have evidence of light being a wave. So I guess it's both. So Bohr was the one who kind of came up with the truce. And then we have another guy named de Broglie. And de Broglie was about 23 years old. He was a college student, and he believed in the beauty or symmetry of nature. And he said, well, if light, which we thought was a wave, can be a particle, that means particles can probably be waves. So even though we do not think of ourselves as a wave, de Broglie says we can be a wave. And our wavelength would be equal to h over mv. All right, that's more than enough that you need to know. All right, last one, give a brief description of the photoelectric effect. So the photoelectric effect was actually discovered by another scientist, but it was explained by Einstein. So if you have a piece of metal and you shine light on the metal, electrons that are in the metal can be released. So I'll make the electrons look like they're being released. And so these electrons are released. And if we catch those electrons in a wire, we can then use those electrons to create a circuit. And so this is called the photoelectric effect. And basically it's the precursor of a solar cell or a solar panel. Okay, so we talked about everything on the list. I'm not going to talk through nuclear physics and Einstein because that's our current unit. And again, I know I don't have specific questions here for you, but you can get those off old tests. I just wanted to review the concepts and the topics that are going to be on the exam so that you can use these as tips and tricks and hints as to what you should put on your piece of paper, front and back. If you have any specific questions, please bring them to class on our review day. I hope this helped.